While you were fast asleep last night, a cosmic-level alarm was traversing 13 billion years of darkness, quietly arriving at Earth. Its source was a star that died violently in the universe's infancy. A gamma-ray burst. Within mere seconds, it released more energy than the sun will in its entire lifetime, and today, for the first time, humankind has clearly heard this final cry from 13 billion years ago. It not only illuminates the universe's earliest darkness, but may also hold the codes for matter, life, and even our own origins. Welcome to a cross-temporal dialogue with the universe's first light. The following content is highly soporific. You must listen attentively and sleep quietly. In this vast and boundless universe, every faint beam of light is a piece of history that has wandered to this day. In 2024, a silent voyage began quietly, an astronomical satellite jointly developed by China and France, carrying the most advanced detectors on Earth, broke through the atmosphere and soared into space. It did not come for noise. It listens for one thing only: two signals from the farthest reaches of the cosmos, those unheard for hundreds of millions of years. This satellite was given an extraordinary mission: to detect one of the universe's briefest, most violent, and most mysterious phenomena, gamma-ray bursts. So, how can we understand these gamma-ray bursts? Gamma-ray bursts, or GRBS in English, pronounced gamma burst. Say it with me again: gamma burst. It is one of the most violent energy release phenomena known in the universe. A typical gamma-ray burst, within just a few seconds to tens of seconds, can release radiation equivalent to the total energy output of the sun's entire lifetime. This is a truly astonishing phenomenon. Scientists classify gamma-ray bursts into two main types. The first, short-duration gamma-ray bursts, meaning they last less than 2 seconds, usually produced by the merger of two neutron stars. The second, long-duration gamma-ray bursts, lasting more than 2 seconds, often originating from the collapse of a supermassive star into a black hole. The gamma-ray burst captured this time by the Sino-French satellite belongs to the short-duration type. It signifies that in the early universe, there may already have been dense celestial objects, such as neutron stars or primordial black holes, undergoing violent interactions. Gamma rays themselves are a form of electromagnetic wave with extremely high energy, far more powerful than visible light. Because they can traverse vast cosmic distances, gamma-ray bursts have become important targets for probing the ancient universe. However, gamma-ray bursts are also extremely rare and fleeting. On Earth, even with thousands of astronomical telescopes watching the sky, the probability of capturing a truly clear gamma-ray burst is extremely low. Therefore, this capture of a 13-billion-year-old gamma-ray burst is not merely a lucky encounter. It represents the scientists' patient and technologically advanced exploration, perhaps behind the cold data. What truly moves us is such a miracle of resonance with the distant heartbeat of the cosmos. Gamma-ray bursts, the most violent eruptions in the cosmos, are brief and dazzling, like the final roars of stars. The energy released in a single gamma-ray burst often exceeds the sun's total lifetime energy output. Within just a few seconds, they are born from the death of stars and from the most violent collisions in the universe. This time, what the Sino-French satellite captured was a special gamma-ray burst, a signal from 13 billion years ago. 13 billion years, what kind of concept is that? At that time, the universe was only a few 100 million years old. Still in its adolescence, the Milky Way had not yet fully formed. The Sun was far from being born. Earth was merely a possibility amidst future cataclysms. 10 wonders, filling the universe with the earliest gas clouds, the kindling of the first stars, and this beam of gamma rays was precisely the explosive finale of a massive star from that era. It collapsed, tore apart, releasing unimaginable energy, a piercing light, breaking through the darkness, traversed billions of light years of cold silence, heading toward the future. But the universe does not easily reveal its secrets on this long journey. This beam of light passed through countless interstellar dust clouds, grazed expanding space-time, and passed by repeatedly reshaped galactic structures. It could have been annihilated, bent, or obscured along the way, but it was not. It persisted in silence, finally arriving at this pale blue planet at a tiny, fleeting detection window. When the data transmitted to the ground receiving station, researchers noticed the anomaly immediately. This was no ordinary gamma-ray burst. Its energy curve, its duration, its redshift, everything pointed to one shocking fact. This was a signal that had traversed almost the entire history of the universe, and it came from an era almost beyond our imagination. This is not just a success in astronomical observation, it is a breakthrough in our dialogue with the earliest universe. Through this gamma-ray burst, we get a glimpse of how the first stars were forged in extreme environments, how they burned themselves out, ending their brief lives in spectacular explosions, and how they scattered heavier elements into the sea of stars, sowing the seeds for everything that followed, including life. Among the matter released in gamma-ray bursts, there is carbon, oxygen, iron, the very foundations that, billions of years later, would form Earth's mountains, oceans, and life. One could say that every part of our bodies, every grain of dust, bears a deep and subtle connection to such ancient cosmic explosions. For scientists, the significance of this observation is even more profound. It helps us verify theories of early stellar formation in the universe, infer the existence patterns of the first massive stars, and even provides new observational data on dark energy and the universe's expansion rate. Each ancient gamma-ray burst is a timestamp written by the universe itself, and deciphering these timestamps is the process of humanity seeking its own origins. This discovery also proves the importance of international collaboration. In the face of the vast, boundless cosmos, there are no borders, only the shared desire to gaze at the stars. Perhaps you have looked up at the starry night sky, wondering what stories lie behind those countless points of light. The answers are gradually being revealed. In each satellite, each telescope, and each pair of upward-looking eyes, this faint light from 13 billion years ago tells us the universe never stops telling its own story. It's just a matter of whether we are willing to listen. When the Sino-French astronomical satellite received that fleeting light, it was not just a victory for science. It was also a small yet great handshake across the river of time. One end held a lonely star from 13 billion years ago. The other held an ordinary night on Earth in 2025. Between the vast and the minute, between time and memory, you to have heard the voice of the universe, and in doing so found your own direction. Galaxies and nebulae are interwoven by the universe's own threads. But when we find a gap in this grand design, what happens in one place? The fabric of the cosmos seems to have been shaken, leaving behind an almost unfathomably vast expanse of space. Devoid of almost anything, imagine a region of space so vast, so empty, that if you traveled at the speed of light, it would take over 330 million years to cross it. This is roughly 23 times the size of our Milky Way. It is an extremely barren region, with an astonishingly low average density of galaxies, challenging our understanding of cosmic structure. This is not science fiction. It is a very real and mysterious feature of our universe, a cosmic void. It is an enigma of the cosmos, a dark abyss that stretches beyond our understanding of the universe and its formation. To truly grasp the significance of our journey into this cosmic void, we must first travel back in time to when the concept of cosmic voids was but a faint shadow in the minds of astronomers. In the late 18th century, astronomy entered a new era. With the invention of the telescope, astronomers began mapping the cosmos with unprecedented precision. Yet, as they charted the bright, extended region of the Milky Way, they could scarcely imagine that beyond their view existed such vast cosmic structures. Let's move to the 20th century. The advent of modern telescopes and observational techniques revealed the universe to us in unprecedented ways. Astronomers realized that our Milky Way is but one of billions of galaxies scattered across an unimaginably vast cosmos. When mapping the distribution of galaxies, they began to notice something strange in some regions. The number of galaxies was far fewer than expected. These areas, initially thought to be observational anomalies, later came to be known as cosmic voids. It wasn't until the latter half of the 20th century that the concept of cosmic voids truly took hold. In the 1970s and 1980s, studies of redshift, a method for measuring galactic distances, revealed the large-scale structure of the universe. Galaxies were not randomly scattered. They seemed to form a kind of cosmic web, with vast void regions between them. As digital technology and more powerful telescopes emerged in the late 20th and early 21st centuries, our understanding of these voids expanded. Projects like the Sloan Digital Sky Survey and the DF Redshift surveys mapped detailed 3D charts of the cosmos, fully revealing cosmic voids. From the initial discoveries of early astronomers to today's advanced instruments and methods, the discovery and exploration of cosmic voids is a fascinating chapter in our quest to understand the universe. However, despite our progress, these vast kingdoms of nothingness still puzzle scientists. The Great Void remains a unique enigma. Meanwhile, as we delve deeper into its mysteries, we can't help but ask, how did it form? As astronomers probe deeper and more precisely, they discovered an interesting pattern in galactic distribution. Firstly, on the largest scales, Galaxies are not randomly distributed in the universe. Instead, they cluster together, forming a complex network of cosmic structures. This network is often called the cosmic web, composed of galaxy clusters, filaments connecting them, and the vast void spaces between. Voids appear as extensive regions with far fewer galaxies than average, standing in stark contrast to the dense clusters and filaments of the cosmic web. Confirming this large-scale structure of the universe was a crucial milestone in understanding cosmic voids. These voids are not merely absences of galaxies. They are integral components of cosmic architecture. Now that we've navigated the cosmic maze leading to the discovery of cosmic voids, let's dive into one of the most mysterious voids confirmed to date. One so immense it's called the Great Void. This region is the Boat's Void, named after the constellation where it lies. The Boat's Void was discovered by astronomer Robert Kirshner and his team. It is one of the largest known voids in the universe. The Boat's Void is not only huge, but also exceptionally empty. In a region of space where one might typically expect to find 10,000 galaxies, the Boat's Void contains only about 60. Imagine it as a cosmic desert, a vast blank expanse within the galaxy-rich cosmos. The existence of such a massive void challenges the cosmological principle. According to this principle, on sufficiently large scales, the universe should appear roughly the same in all directions. The mystery of the Boat's Void goes beyond its size and emptiness. For example, some galaxies within the void are arranged in peculiar-to-like structures of feature not yet fully explained. Continuing our journey through the cosmic ocean, our next stop is another striking void with a dramatic name, the supervoid. This is the Eridanus supervoid. The Eridanus supervoid, observed in the constellation Eridanus, is not just a void but a supervoid. It is one of the largest structures ever discovered in the universe. To put it in perspective, this supervoid has a diameter of about 1 billion light-years. Traveling at light speed, it would take a full billion years to cross it. The Eridanus supervoid is not only immense, but also extremely barren. While it's not completely devoid of galaxies like the Boat's Void, its vast expanse is anomalously poor in galaxies compared to the rich cosmic regions around it. But what makes the Eridanus supervoid particularly intriguing is not just its size or emptiness. This supervoid is linked to a mysterious cosmic phenomenon known as the CMB cold spot. The CMB cold spot is an anomalously cold region in the cosmic microwave background, the afterglow of the Big Bang. Some scientists speculate that this cold spot might be caused by the Eridanus supervoid. The massive void could induce an effect called the integrated Sachs-Wolf effect, where photons lose energy traversing the void, creating a colder spot in the CMB. Continuing our voyage through the cosmic desert, we encounter another mysterious void region, the Canes Venatici supervoid, located in the constellation Canes Venatici. This supervoid powerfully illustrates the scale and vastness of our cosmos. Like other supervoids, the Canes Venatici supervoid lies in a region of space with significantly fewer galaxies than expected to grasp its scale. Consider its incredible diameter of 120 million light-years. It's like a patch of cosmic desert within a galaxy-rich forest. The Canes Venatici Supervoid is a profound expanse of emptiness. Although the size and emptiness of the Canes Venatici Supervoid are captivating, questions remain. How did such an enormous void form? What process in the early universe could produce such a vast region of emptiness, while the exact process leading to void formation remains unanswered? Several compelling theories have been proposed. The first potential scenario involves the concept of cosmic inflation. It is thought that shortly after the Big Bang, the universe underwent a period of rapid expansion or inflation, stretching space itself. During this inflationary epoch, quantum fluctuations may have been amplified to cosmic scales, leading to regions of higher and lower density in space. Over billions of years, matter under gravity's pull clustered into higher density regions, forming galaxy clusters and filaments, while lower density regions evolved into cosmic voids. A second theory involves dark energy, a mysterious force causing the universe's accelerated expansion. Dark energy may have played a role in void formation by pushing galaxies away from lower density regions toward higher density ones, effectively inflating these voids over cosmic time. Finally, cosmic void formation might also be linked to large-scale structure processes in the universe. As matter clumps under its own gravity to form structures like galaxies and clusters, voids naturally emerge in the remaining space. This process is akin to bubbles forming in rising bread dough. Just as dough solidifies around air pockets, cosmic matter forms structures around void spaces. These are just some of the theories scientists explore to explain the formation of these cosmic anomalies. But however vast and mysterious these great voids are, they are but one piece of a complex cosmic puzzle that scientists are still piecing together. The exact processes leading to void formation are shrouded in mystery, and uncovering these secrets is a daunting task. One major challenge is the sheer scale and complexity of the universe. The cosmos is immeasurably vast, teeming with countless galaxies, each with its own properties. Understanding how they interact and influence larger cosmic structures is a monumental endeavor. Another difficulty lies in the elusive nature of dark matter and dark energy. These invisible forces are thought to play crucial roles in cosmic structure and void formation. Yet, our understanding of them remains limited. Without a clear grasp of what dark matter and dark energy truly are, understanding their impact on void formation remains a huge challenge. Despite these obstacles, research in this field is active and evolving. Scientists employ increasingly advanced tools and techniques, from sophisticated telescopes to complex computer simulations, to probe the mysteries of great voids. Large observational projects like the Sloan Digital Sky Survey map the distribution of galaxies in the universe, providing invaluable data for studying cosmic voids. Computer simulations, meanwhile, can recreate cosmic evolution under different conditions, helping test theories of void formation. In exploring the origins of these vast cosmic voids, each new discovery, each piece of data, brings us one step closer to understanding. Great voids hold profound implications for cosmology and our understanding of the universe and its structure. Firstly, they offer unique perspectives on the roles of dark matter and dark energy, those elusive yet dominant components of the cosmos. Dark matter, though invisible, forms the scaffolding of large-scale cosmic structure. Its gravitational pull helps shape the cosmic web of galaxies and voids. The very existence of these vast voids suggests that dark matter played a key role in forming the universe we observe today. Meanwhile, dark energy, the mysterious force driving the universe's accelerated expansion, may also play a crucial part in the development of these voids by pushing galaxies away from lower density regions. Dark energy can inflate voids over cosmic timescales, but the significance of cosmic voids goes further. Studying these voids can provide vital information to refine current cosmological models and theories. For instance, the sizes and distribution of cosmic voids can serve as unique tests for cosmological models. If a model accurately predicts the properties of these voids, it gains credibility. Conversely, any mismatch between model predictions and observations might indicate a need for refinement or even a new physical theory. Indeed, these great cosmic voids, once thought to be mere empty spaces, hold an important place in our quest to understand the universe. But what if these voids are more than just empty space? Their study has sparked theories that reach beyond our familiar cosmos, touching realms of speculation and the extraordinary. One such theory involves the concept of parallel universes or a multiverse, the idea that our universe may not be alone, but one of many coexisting realities. According to some theorists, great voids might not be just vast empty spaces. In fact, they could be interfaces or passages to these parallel universes. This hypothesis stems from certain interpretations of quantum mechanics and string theory, which posit the existence of extra dimensions beyond the three spatial and one time dimension we know. If such dimensions exist, they might host myriad different parallel universes, each with its own unique physical laws and properties. In this scenario, great voids could be regions where our familiar four-dimensional cosmos thins out and connects to these other dimensions. It's important to note, however, that this idea is highly speculative. While it offers a fascinating perspective and inspires countless science fiction tales, it is far from being accepted by most of the scientific community to date. We have no solid evidence for parallel universes or extra dimensions. Delving deeper, we encounter the idea mentioned earlier, one that links the vastness of the cosmos with the infinitesimally small quantum world. This concept is quantum fluctuations. In the quantum realm, particles and energy constantly pop in and out of existence, creating a frothing sea of fluctuations. But what do these microscopic phenomena have to do with immense cosmic voids? The answer takes us back to the universe's early stages. Shortly after the Big Bang, during this period, the universe was extremely tiny and in such a state. Quantum effects could have significant influence on cosmic scales. Quantum fluctuations occurring then might have been amplified as the universe expanded. These amplified fluctuations could have led to uneven distributions of matter and energy over billions of years. lower density regions could have evolved into the vast cosmic voids we observe today. In this view, great voids are like ancient imprints of quantum fluctuations from the universe's birth stamp onto cosmic structure. However, it's worth noting that while this theory is intriguing and has some basis in our current understanding of physics, it remains a hypothesis. Testing such a theory is a monumental task, requiring precise measurements of large-scale cosmic structure and deeper insights into quantum physics and cosmology. Yet the prospect of linking the quantum world to the cosmos, connecting the smallest scales to the largest, is deeply alluring. Another captivating hypothesis takes us into the abstract and complex world of topology. Topology is the mathematical study of space and its properties. In the cosmic context, topological anomalies or space-time defects refer to irregularities in the fabric of space-time, like imperfections in a fabric. These defects could represent regions where the normal structure of space-time is disrupted. But where might these anomalies come from? To answer, we must go back to the universe's inflationary epoch, the brief instant after the Big Bang. During this phase of super-rapid expansion, the universe grew exponentially. While this inflation smoothed out the overall distribution of matter and energy, it might also have amplified tiny irregularities in space-time structure, leading to the creation of topological defects. These defects could become regions where matter struggle to gather, eventually forming the vast cosmic voids we know. No exploration of cosmic voids would be complete without considering one of the universe's most mysterious objects, black holes. Specifically, we're talking about primordial black holes. Unlike the black holes we know form from collapsing massive stars, primordial black holes are thought to have formed shortly after the Big Bang. They might have been created by extreme density fluctuations in the early universe. So, what's the connection between these ancient black holes and our great cosmic voids? One idea suggests these voids might be filled with primordial black holes. According to this notion, great voids could be the result of vast numbers of primordial black holes hidden within. Since they don't emit significant radiation, they'd be extremely hard to detect directly. Yet, their presence would exert gravitational effects, effectively clearing out the surrounding regions and forming the immense voids we observe. Another theory links the appearance of great voids to the elusive dark matter. Dark matter, though undetectable by traditional means, is thought to make up about 85% of the universe's matter content. Dark matter plays a key role in shaping cosmic structure, weaving a vast, complex web that interconnects galaxies. These dark matter filaments provide cosmic scaffolding, guiding the formation of galaxies and clusters. But what if something disrupts these filaments? What if a major event or unknown force causes them to collapse or disintegrate? This is where cosmic voids might come into play. According to this theory, the collapse of dark matter filaments could lead to the formation of these immense voids. The collapse would interrupt the flow of matter, leaving behind vast empty regions. So, as we've come to understand, these vast void regions are far from barren wastelands. They are treasure troves of clues and mysteries about the cosmos and its composition. from the formation of large-scale cosmic structure to the behavior of dark matter and dark energy. The enigma of great voids pushes us to rethink our understanding of the universe. While we may not have all the answers yet, each question we ask, each void we explore, brings us one step closer to unraveling cosmic secrets. Remember, whenever you gaze up at the night sky, you're seeing not just stars and galaxies, but also the unseen cosmic voids, the silent sentinels of the cosmos, continuing their eternal watch, guarding the universe's secrets within their vast expanses. When that beam of gamma rays from 13 billion years ago struck the satellite's detector, it was not merely a data point. It was an encrypted letter spanning nearly the entire age of the universe. The sender of this letter was a star that died in the cosmic dawn. The recipient was intelligent life that emerged billions of years later. The letter's content was extremely simple, just a spike of energy, but deciphering it requires the most advanced knowledge of physics and cosmology humanity possesses. Each captured gamma ray burst is like hearing a distant gunshot in the dark forest of the cosmos. We don't know who fired the shot or why, but through the echo of the shot, we can infer the forest's terrain, even guess the shooter's appearance. This is the romance and hardship of gamma ray burst astronomy. It is built on a somber assumption: the most spectacular events in the universe often accompany the most complete destruction. Yet, we rely on these signals of destruction to piece together the story of creation. How stars are born, how they die, how elements are forged, how galaxies evolve, how the ingredients for life are cast from stellar furnaces into interstellar space. Clues to all these questions are hidden in the fleeting, intense light of gamma ray bursts. Therefore, each successful detection is no less significant than a major discovery in cosmic archaeology. What we unearth are not pottery shards and bones, but fossilized energy from the universe's youth. However, deciphering this cosmic fossil is no easy task. A gamma ray burst itself is like a magnificent firework. We only see its brightest flash to understand how this firework was ignited. We need to capture the afterglow that persists long after the flash dims. Following the gamma ray flash, afterglows in X-ray, visible light, and even radio wavelengths often appear. These afterglows are like the slowly dispersing smoke at an explosion site. By analyzing the afterglow spectrum and evolution, scientists can infer the environment where the explosion occurred, the speed and composition of the ejected material, and the total energy released. Is like crime scene investigation, reconstructing the shooting scenario from ballistics, bloodstains, and residue. The extraordinary aspect of the 2024 detection is that it captured a short burst. It is generally believed that short bursts originate from the merger of two dense objects, such as a neutron-star binary. After orbiting each other for billions of years, they finally spiral inward and collide. This process releases intense gravitational waves and a gamma ray burst. The redshift of this detected short burst reveals an astonishing fact. It occurred when the universe was only a few 100 million years old. At that time, the abundance of heavy elements in the universe was extremely low, and the first stars had just formed. So the question arises, could neutron star binaries have already evolved and merged so early in the universe? It's like finding a centenarian couple celebrating their golden anniversary in a town that was just built. Their existence forces us to revise the timeline of stellar formation and evolution in the early universe. Perhaps the death of the first stars was more rapid and violent than we imagined, and the dense remnants they left behind began their cosmic dance of death much earlier. This detection undoubtedly dropped a bombshell on theoretical astrophysicists. It forces us to reconsider just how lively the first few 100 million years of the universe were. Beyond the birth and death of stars and black holes, was it already a bustling world filled with gravitational wave ripples and gamma-ray flashes? Pulling our gaze back from the distant past, a more practical, even slightly chilling, question emerges. What if a gamma-ray burst occurred within the Milky Way, or even closer to us? The answer is, it would be a catastrophe for life on Earth. Gamma rays possess extremely strong penetrating power. If a nearby gamma ray burst were aimed directly at Earth, its high-energy radiation could easily strip away the ozone layer, allowing lethal ultraviolet rays to reach the surface simultaneously. Interaction with atmospheric molecules would produce large amounts of nitrogen oxides, further destroying ozone and potentially causing a global nitrogen oxide haze, blocking sunlight and triggering global cooling. A cascade of effects could likely lead to a mass extinction event, comparable to the dinosaur extinction. Some scientists believe that some past extinction events on Earth may be linked to gamma-ray bursts within the Milky Way. Fortunately, massive stars capable of producing long gamma-ray bursts in the Milky Way are rare. Moreover, their jets are usually highly collimated, like searchlights. Only planets that happen to be in the path of this death searchlight would suffer. The probability is exceedingly low. As for short bursts, their neutron star merger origins are even rarer, and their energy is more focused, making the probability of a direct hit minuscule. So we need not lose sleep over this. The universe's cruelty typically manifests as a spectacular display kept at a safe distance. However, it is precisely the study of this cruel spectacle that might save us in the future. Gamma-ray bursts, especially those associated with gravitational wave events, are natural laboratories for testing extreme physical conditions. In the moment of neutron-star merger, densities are so high that atomic nuclei are crushed, and matter is ejected at near light speeds. The physical processes occurring here are impossible to replicate in any laboratory on Earth. By studying these signals, we are learning the equation of state of matter at ultra-high densities, how relativistic jets are formed and collimated. This knowledge not only concerns the cosmos, perhaps one day it could lead to entirely new energy forms for humanity, or a deeper understanding of matter itself. Returning to that 13-billion-year-old light, its journey continues. After passing through the satellite's detector, it transformed into bits on a hard drive, into charts and scientific papers, into the story we discussed tonight. But its essence is a beam of light finally seen in the era of its departure. There may have been no complex size in the universe to appreciate such brilliance. Its birth was a destruction witnessed by none. Its journey was an eternal, solo voyage until today it encountered us. We built machines, extended our senses, just to say, at the moment of its arrival, we have seen. Perhaps this is the deepest romance of scientific exploration. In this indifferent universe, we seek echoes, seek imprints, seek those messengers that traverse vast stretches of time and space, waiting only for a kindred spirit to understand. Gamma ray bursts are the alarm bells of the cosmos, and also its epic poems. They tell us that creation and destruction are two sides of the same coin. The most brilliant light is born from the deepest darkness. The most enduring elements are forged in the most violent explosions. The iron in our bodies, the oxygen we breathe, the carbon on which life depends, all come from some stellar death event in the distant past. We are stardust, the ashes of cosmic explosions, miracles gathered by gravity through countless accidents, and endowed with self-awareness. Next time you look up at the night sky, gazing at those calm points of light, remember many of them long ago experienced or witnessed cataclysmic moments of life and death like gamma ray bursts. That calm is an illusion. The universe has never been calm. It is always burning, exploding, colliding, being born and dying, and our fragile planet happens to float in a quiet harbor amid this eternal storm, allowing us to look up, to wonder, to question, to listen to the light from the abyss. When the light of a gamma ray burst penetrates billions of light years to reach our eyes, it brings not just energy, but a profound inquiry into the nature of the cosmos. If the universe is an unending cycle of life and death, then gamma ray bursts are the loudest heartbeats in this cycle. They remind us that the universe is not a static stage, but a dynamic, violent, ever self-remolding living entity. Stars are not eternal. They are born from the gravitational collapse of nebulae, live their lives in the nuclear fusion fires at their cores, and ultimately, in the form of supernovae or gamma ray bursts, hurl most of their substance back into interstellar space. This ejected matter, rich with heavy elements forged in stellar furnaces, mixes into the next generation of nebulae, becoming the raw material for new stars, planets, and even life. From this perspective, a gamma ray burst is not an end, but a critical link in the cycle, a violent process of cosmic metabolism and upgrading. Without such outbursts, the universe would remain forever in a monotonous state of only hydrogen and helium. There would be no rocky planets, no liquid water, no complex carbon-based chemistry, and we would not exist. Therefore, when we detect an ancient gamma ray burst, we are not merely observing an old destruction. We are actually tracing the origin story of the very matter that composes us. That light from 13 billion years ago may carry the forging information of atoms that later formed our solar system, Earth, and our own bodies. What a marvelous connection! Our existence is intimately linked to a distant, destructive explosion in the universe's extreme infancy. This gives new meaning to the saying, life is a cosmic accident. Perhaps life is not an accident. It is a natural product of cosmic material evolution, an inevitable emergence within the complex chemical environment created by the stellar life-death cycle. It just takes time, countless explosions and settlements, unimaginable patience, and the universe has no shortage of time beyond contributing matter. Gamma ray bursts hold another significant meaning for the cosmos. They are lighthouses illuminating the Dark Ages about 380,000 years after the Big Bang. As atoms form, photons could travel freely, creating the cosmic microwave background radiation we detect today. Thereafter, the universe entered the Dark Ages. No stars, no light sources, only neutral hydrogen and helium gas. Not until the first stars and galaxies formed did this darkness end. The first stars were often massive, short-lived blue giants that likely ended their lives in violent supernovae or gamma ray bursts. Therefore, detecting gamma ray bursts from the universe's extreme infancy is like finding a pinprick momentarily piercing the curtain of the Dark Ages, allowing us a glimpse of how the universe's earliest light sources were ignited. The intense ultraviolet light from these early bursts would also rayonize surrounding neutral hydrogen gas, gradually clearing the cosmic fog and paving the way for subsequent galaxy formation. One could say gamma ray bursts are not just cosmic destroyers, they are also catalysts for the cosmic enlightenment, using their destructive light to dispel the darkness of the universe's childhood and herald the dawn of the galactic era. From a technical standpoint, capturing and analyzing such distant gamma ray bursts is itself a struggle against limits. Gamma rays cannot be focused by traditional optical telescopes. Detecting them requires special instruments like scintillation detectors, which convert high-energy gamma photons into visible light pulses for recording. Because gamma ray burst directions are unpredictable and their durations extremely short, satellites must maintain a constant -1 skywatch in orbit. Upon a trigger within milliseconds, they must initiate multi-wavelength coordinated observations, mobilizing global telescope networks to target the burst region and capture its precious afterglow. This is a highly automated, globally coordinated, astronomical rapid response force. Each successful multi-wavelength observation is a testament to international collaboration and technological prowess. Like the 2020 Fresno French satellite, it represents humanity launching detectors into space, setting up specialized ears to listen to the most violent sounds from the cosmic depths. This act of listening itself is a silent tribute to the cosmic might that blooms and fades alone in unknown darkness. From a philosophical angle, gamma ray bursts reveal the duality of the cosmos. One faces ultimate creation. In stellar cores, the high temperature and pressure from gravitational compression fuse light elements into heavy ones. This is creation. The other side is ultimate destruction. Stellar fuel exhausted. Gravitational collapse triggers explosion, tearing the star apart. This is destruction, yet it is this ultimate destruction that completes the final link of the creative cycle, scattering the created heavy elements, enabling new creation. Without destruction, creation would be closed, meaningless. Without creation, destruction would be hollow, meaningless. Gamma ray bursts perfectly embody this dialectic in destroying themselves. They create the possibilities for countless future worlds. Human civilization seems to echo a similar rhythm. Our thoughts are art, our technology, are these not a form of creation? And wars, conflicts, the collapse of systems, are these not a form of destruction? Yet historical experience tells us that new creation often emerges from destruction. Civilizations are reborn from ruins. Ideas burst forth after constraint. Perhaps this is a microcosm of cosmic laws in human society. Understanding the grand cycle of the cosmos might grant us more detachment, more resilience toward our own situation. Finally, let's return to the initial sense of wonder. That light from 13 billion years ago. When it set out, the universe was in its infancy. When it arrived, thinking life existed on Earth, the span of time between exceeds twice the age of Earth. After such an immensely lonely journey, it was not swallowed by the void, not buried by dust, but just happens to be caught by a tool made by a species that, in the history of evolution, has just learned to gaze at the stars and given meaning by this species. Isn't this one of the most astonishing coincidences in the universe? Science tells us this is perhaps a matter of probability, one occurrence among countless accidents, but the soul tells us this is a form of connection. A glance of the universe recognizing itself. We understand the universe through gamma ray bursts, and the universe, through our understanding and awe, completes a self-awareness of its own magnificence and cruelty. We are not just stardust. We are also the eyes through which the universe sees itself, and the brain through which it thinks of itself. The story of gamma ray bursts continues. In the future, more sensitive detectors will be launched, and we will hear more clear heartbeats of the universe. Perhaps one day, we will decode all the secrets within gamma ray bursts about gravity, about matter, about space-time, and on that day, we will have answers closer to the essence of the eternal question. Who are we, and where do we come from? Until then, let us maintain this posture of listening, sustain our curiosity, and offer the light in the abyss, because every violet probe into the universe is a tender inquiry into the very roots of our own existence. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.